Hello, I'm Desmond Edagese, and I welcome you to maths class. Today we'll be looking at a very interesting topic, introductory calculus. And under introductory calculus, we'll be learning about the integration of algebraic functions. Remember, we have so many functions. We have trigonometric functions, we have logarithmic functions and all, but today we'll be focusing on algebraic functions. In our subsequent classes, as we go higher in maths, we'll learn about how to find the integration of other functions. Let's go on into our class for today. These are some of the things that we expect to have learned at the end of our class today. Number one, we'll be getting a brief introduction to exactly what calculus is all about. Next, we'll find out what integration is. Also, we expect to have learned the basic rules that govern integration. Next, we'll see some standard integrals. And finally, we'll learn about how to use different methods to integrate algebraic functions. Now, calculus, like we learned in our earlier class in differentiation, is the mathematical study of change. We said in that class that calculus is divided into two main branches: differentiation, which is also known as differential calculus, and integral calculus, which is also known as integration. Integration is what we are going to be focusing on for today. So now, what exactly is integration? Integral calculus or integration, so we said calculus, from the Latin word, means small stone. We said it is named a small stone because it looks at such issues of change as little bits of stones that are studied separately in order to better understand it. Well, integral calculus joins or integrates those small pieces together to tell us how much of something is made overall by a series of little changes. Now, there is a particular sign that is prevalent in integral calculus as we go on further in our study. That sign is something like this. This sign, the integral sign, basically stands for an S, but written in a stylish manner. Let's go on as we further understand what integral calculus is. Integral calculus is also divided into two branches. We have definite integrals and indefinite integrals. In this class today, we'll be focusing on indefinite integrals. Definite integrals are integrals that have upper and lower limits. They are used mostly in finding the exact value of the area under curves, while the indefinite integrals, which we'll be focusing on, come without limits. The operation of integration is the reverse or the opposite of differentiation. In our class before now, we learned that differentiation is the rate of instantaneous change of a quantity. That is the derivative of a quantity with respect to x. Well, integration is the opposite of differentiation. Hence, integration is also known as anti-differentiation. If, for instance, a derivative f prime x is given and you were asked to find what the original function f of x was, such questions are easily answered with an indefinite integral. So we simply find the integration of that derivative and we'll get back our original function. Let's take a typical example. If we have a derivative, 2x, and we were asked to find the original function from whence this derivative was gotten, to get our original function back, we have to integrate 2x, and when we do that, we'd have our original function as x squared. So, x squared is the original function of 2x. Let's go forward in our class, and then we'll see better illustrations of what we are trying to say. For example, if we have a derivative 3x squared, and we are also asked again to find the original function from whence we got this derivative. Of course, we know that we have to integrate this. When we do that, we would have our original function as x cubed. So if you differentiate x cubed, that's what it means. You would have 3x squared. Hence, we say integration is the opposite of differentiation. But the integral is written as x cubed plus a constant c. So the integral is not just written as x cubed, but with a constant c. Let's find out why. Now, if this is our original function, right? Original function, and this is our derivative, it therefore means that if we differentiate x cubed, we would have 3x squared. What if we differentiate x cubed plus 4? If we remember our differentiation formula, using the product rule, we would have what? 3x squared. Differentiation of a constant 4 will give us what? 0. Same way, if we differentiate this function here, x cubed plus pi, we would also have 3x squared. The differentiation of this constant is also 0. Same with our function here also. If we differentiate this function, we would also have 3x squared, because the differentiation of this constant 27.3 will also give us 0. It therefore means that any constant could have been added to x cubed, and it will still give us our derivative 3x squared. And hence, when we have an integral, which we said is the opposite of differentiation, we always add c. C stands for our unknown constant. However, from these examples, whatever the constant is, our c here will stand for the unknown constant. We call that constant the constant of integration. As we go on in our class, we'll find out that for every integral found, we always add the constant of integration. Let's go on. Now, this is what a typical representation of what an integral looks like. The indefinite integral is the antiderivative, that is, a function f whose derivative is the given function y. It means that the indefinite integral, which is our antiderivative, is the opposite of our differentiation. It gives us the original function from whence a derivative is gotten. So f of x here stands for the integration variable, while our c, like we just learned, stands for our constant of integration. This is our integration sign. We've learned that it's a stylish S, so there's nothing really special to it. It is called the integral symbol. It's just an elongated S, which stands for sum. Remember, we said integral talks about integrating, summing up little parts to find out exactly what the sum of a part is. While our function under our integral symbol is called the integrand. The integrand. All right, let's go on. Now, there are basic rules that govern integration. One of the first rules we will learn about today is the integral of a constant. When we have a constant, say c, for instance, we write the integral of c as integration c dx. The dx lets us know that we are working with respect to x. This would give us our constant along with a variable x plus our constant of integration. So the rule states that the integral of a constant is that constant times x plus a constant, that is a constant of integration with the capital C. Let's take some typical simple examples. if we're asked to find the integral of 4, 4 is a constant. From our formula, we simply say the integral of 4 dx is what? 4x plus c. So we simply multiply our constant 4 with x and add, of course, our constant of integration. Also, if we're asked to find the integral of 9, same way, we simply say the integral of 9 dx is what? 9x plus c. Quite simple. Now, another basic rule of integration is the integral of a power of x rule. The integral of a power of x rule. Whenever we have a variable that is raised to a power and we're asked to find the integral of that variable or the integral of that function, we'll simply add 1 to our power and also divide our function all over that power plus 1. So for the integral of a power of x, add 1 to the power and divide by the new number that we have. Let's go on to look at some examples to better understand. If we're asked to find the integral of x raised to power 5 dx, to do this, following our rule, we'll simply add 1 to our power here, which is 5 plus 1 will give us 6, and we'll divide all of that, the variable x raised to power 5 plus 1, all over the same new number we get, 5 plus 1. All of that, of course, we add plus c, which is our constant of integration. So if we work this out, we'd have x raised to power 5 plus 1 is x raised to power 6, all over 6. So the integral of x raised to power 5 is what? X raised to power 6 all over 6 plus c, which is our constant of integration. Let's take a look at another example. If we were asked to find the integral of 4x cubed dx, this situation brings us a point that is very important when we have such situations where you have a constant multiplied to the function we are looking for the integrand for. This constant goes out. That is, in this case, our 4 would go outside of the borders of our integral, while the function remains, which is what? X cubed dx. So as we go forward in our class, we'll come across many situations like this. Remember to always take the constant outside of the integral sign while you continue to find the integral of our function. So let's go on. For this case, we would have 4 go out, and that would give us 4 times the integral of x raised to power 3. Following the rule that we just learned, the integral of a power of x rule would be x raised to power 3 plus 1 all over 3 plus 1. And of course, we always add the constant of our integration. If we work this out, we would have 4 times x raised to power 4 all over 4 plus c. 4 cancels out, and of course, we have x raised to power 4 left plus c. This is the integral that we seek. Let's look at some more rules. Now we have another rule which we call the integral of the sum and difference rule. Quite similar to the rule we had in the case of differentiation. If you are asked to find the integral of the sum or difference of functions f of x plus or minus g of x dx, we'll simply find the separate integral of our function f of x and add or subtract it, as the case may be, with also the separate integral of our function g of x. Basically, it states that to integrate a sum or a difference, first integrate each summand individually, then add or subtract the resulting integrals. Let's take some typical examples. If we're asked to find the integral of 3x squared plus root 5x plus 2 dx. This is a typical situation. How do we go about this? We've learned from our rule that we need to find the integral of each summand. So 3x squared is a summand, root 5x is another summand, while 2 is another summand. Let's quickly find their different integrals. Now, to solve this, we'll simply find the separate integrals of each summand. Here we have 3x squared as one summand, root 5x as another summand, and 2 as another summand. And as we can see, we'll find their integration separately. The integration of 3x squared dx, the integration of root 5x dx, and the integration of 2 dx. The integration of 3x squared dx will have 3 out of our integral because it is a constant. We have x squared dx remaining as our integral. Next, we also have root 5, which is also a constant. We take it out, and we have our root x dx remaining within our integral. Lastly, we find the integral of 2. Now let's go ahead and do our integrals. The integral of x squared dx would give us x. We'll add 1 to our power, which is 2 plus 1. And then we'll divide all of that by the new number 2 plus 1, which is 3. So we have x cubed all over 3 as our integral. Remember, we have 3 outside of the integral, and that means we have 3x cubed all over 3. And of course, 3 cancels 3, and we have x cubed left. Next, we have root 5, which is outside of our integral. The integration of root x would give us x raised to the power 3 over 2 all over 3 over 2. Remember, our root here is same as saying x raised to the power half. When we add 1 to half, we have 3 over 2. We also divide all of that by 3 over 2. So we have root 5, which is outside of our integral, multiplied by x raised to the power 3 over 2. Remember our root here, our root x, also means, using the laws of indices, x raised to the power half. If we add 1 to half, we have 3 over 2. Hence, we have x raised to the power 3 over 2, all divided by 3 over 2. Lastly, the integral of 2, we said the integration of any constant would give us that constant multiplied by x, and hence we have 2x. And to crown it all, we add our constant of integration plus c. Now let's simplify what we have here. Of course, we've cancelled out our 3. We have x cubed here. And over here we have 2, which comes up here to give us 2 root 5x raised to the power 3 over 2 all over 3. And lastly, again, we have 2x plus c. So hence, we have our answer here. Let's take a look at another example quickly. If we're asked to find the integration of x squared minus 6x minus 13 dx. To do that, again, we'll find the individual integrals of each function within our integral, and then we'll go ahead to subtract them. So to quickly do this, we'll have the integral of x squared dx minus the integral of 6x dx, also minus the integral of 13 dx. If we simplify this, we'll still have our integral x squared dx. 6 is a constant, and hence 6 goes outside of our integral, remaining the integral of our x dx. Next, we find the integral of 13 dx. Now, let's simplify our equation. To find the integral of x squared dx, that would give us x cubed all over 3 minus 6 outside of our integral times the integral of x dx will give us x squared all over 2 minus the integral of 13 dx will give us 13x, and of course we add our constant of integration. Further simplifying, we have x cubed over 3 minus 6 divided by 2 here would give us 3. Hence we have 3x squared minus 13x plus c. So our final answer is x cubed over 3 minus 3x squared minus 13x plus c. Now here is a list of some standard integrals. These are integrals that over the course of the study of integration you may come across. From knowing them, you can easily apply these integrals to get your answers when you come across problems in the future. Let's quickly take a look at some of them. When you have k, where k is a constant, if we integrate k dx, what we have is k multiplied by the variable x plus c. We said c is a constant of integration that is always added to all our integrals. Next is when we have a variable x raised to a power n. As long as our n is not equal to minus 1, to find the integral of x raised to the power n, we'll add 1 to our power. So we have x raised to the power n plus 1. And we divide all of that by the new number that we get, which is n plus 1. Again, we add our constant plus c. Next, the integral of 1 over x will give us ln x plus c, which is our constant. The integral of exponential raised to a power x will give us the same exponential raised to a power x plus c. The integral of a constant multiplied by a function would give us the constant outside of our integral. We've seen examples before now, and then we further go on to find the integral of our given function. So the constant stays outside of the integral, while the integral is found for the function. The integral of an exponential raised to a power ax, for a is not 0, is the integral of a, where a is a constant, x dx, which is equal to exponential raised to the power ax all over the constant a plus c. Let's go on to learn about certain methods of integration. Now, integration has methods that are used depending on the kind of function that we have to integrate. One method that is popular and used regularly is the method of substitution. This method is used to find the integration of any product that is a composite function, that is the function of a function. We learned about such functions in our class in differentiation, multiplied by the derivative of the inner function. And this is an example of what we've verbally spoken so far. The integration of the function of a function multiplied by the derivative of the inner function is found in a special manner. We equate our inner function as u, hence our equation becomes the integration of f du, while we equate the derivative of that inner function, which is g prime x dx, as du. When we have this kind of situation, we more easily solve it to get our answer. Let's take a look at some examples to better understand the concept. Now, there are two categories of questions where we normally make use of integration by substitution. We've learned that when we have a function that is the function of a function, that is, it has an inner function along with an external function multiplied by the derivative of the inner function, we make use of integration by substitution. Sometimes we have such clear-cut cases where we will actually see the derivative of that inner function along with our function. But sometimes we do not get that. This is one of the situations where we don't have such exact times, but we can also make use of the integration by substitution. These are some of the simple steps we take. First, we convert whatever our question is into this format, that is the integration of the function u du. We do that by substituting u for our gx. Next, we also substitute our du for the derivative of our inner function g prime x dx. Next, we evaluate the function f of u du to get our integrand. And lastly, we replace u by our original gx in f of u. Let's take some examples to better understand the steps we have just enumerated. Now, if you were asked to find the integral of the function x plus 4 raised to a power 5, from our class in differentiation, we learned about such functions, which we called function of a function. It has an inner function and an external function. Let's see if we can solve this using the steps we just enumerated. Quickly, we say let u be our inner function. So u is x plus 4. The derivative of u, which is du dx, here is 1. Because the derivative of 4, which is a constant, is what? 0. So we have our x, also the derivative of x as 1. Du dx is 1. But remember, we want to replace our dx here along with any derivative of our inner function, if it is available. That is, that derivative of our inner function multiplied dx with du. But we also learned that sometimes we may not have that exact derivative, but we can manipulate to get that derivative. Let's see how here. So we have our dx. If we do a cross multiply here, we'll have dx equal to du. So du can simply replace our dx. So now we have all we need to impute into our formula. Remember, we said we need to change this into a workable one that appears in this formula. So we have the integral of f of u du. We have equated our u to be the inner function, and now we have our du as dx. So we go ahead to impute our values. U will impute in here as u raised to power 5, and our du, of course, replacing dx. So we have integral of u raised to power 5 du. Next, we apply our power rule. If we apply our power rule here, we would have u raised to power 5 plus 1 all over 5 plus 1. Of course, plus c, which is our constant of integration. This would give us u raised to power 6 over 6 plus c. Finally, we replace our u by our original function, which is x plus 4. So we have x plus 4 raised to power 6 all over 6 plus c. This is our answer. Let's also take a look at another example that is slightly different. Now, if we are also asked to find the integral of 2x plus 3 all raised to power 4 dx, how do we go about this? Again, we need to transform this into a workable one where we would have f of u du. Let u be our inner function, 2x plus 3 here. The derivative of u, that is du dx, of our function u here would give us 2. So we have du dx is equal to 2. But remember, we need to replace our dx here. So we have dx, if we cross multiply, would give us du all over 2. It means that 1 over 2 du is what we will use to replace our dx. So now, to get our equation, we simply have u raised to power 4. Our du is what? 1 over 2 du, which is du over 2. So this becomes our workable integral. And again, we take out our constant. So half goes out while we go ahead to integrate our u raised to power 4 du. To integrate this, we would have 1 over 2 multiplied by u raised to power 4 plus 1 all over 4 plus 1 plus c. So we have 1 over 2 multiplied by u raised to power 5 all over 5 plus c. If we multiply 2 by 5, we would have 10. But our u here, remember, would also have to replace it with the original function, which in this case is what? 2x plus 3. So if we replace our function here, we'll have 2x plus 3 raised to power 5 all over 10 plus c. And this is our final answer. Now let's take a look at the other type of question that we may get where we need to apply our integration by substitution method. Again, we follow the same steps. We first convert whatever integral we're given to be f of u du by substituting u for gx, which is our inner function, and du for the derivative of our inner function dx. Next, we evaluate this, and then finally we replace our u by the original function gx. Let's take a look at a typical example. If you were asked to find the integral of 4x plus 3 raised to power 10 multiplied by 4 dx. How do we go about this? Again, we'll quickly equate u to be our inner function. U, therefore, is 4x plus 3. The derivatives of our function u, which is du dx, would give us 4. If we did a cross multiplying, we'd have du, which we seek to replace our derivative of inner function multiplied by dx. So our du becomes 4 dx. Now notice that in our original question, we already have that within our question, 4 dx. So that's why we said there are two kinds of questions where we make use of our integration by substitution. In some cases, we already have those derivatives, and in some other cases, we have to derive them. So we do a simple substitution in this case to get the simpler integral that we desire. The integral of f of u, therefore, would be the integral of u raised to power 10 multiplied by du. Du, of course, is 4 dx, which we have here. So we simply write out our simpler integral. And of course, if we worked on this, we would have u raised to power 10 plus 1 all over 10 plus 1 plus c, which would give us u raised to power 11 over 11 plus c. Lastly, we'll impute back the original function of u, which is 4x plus 3, into our answer here to give us 4x plus 3 raised to power 11 all over 11 plus c. And this is our answer. Let's take a look at another example. If we are asked to find the integral of 4x all over root 2x squared plus 1 dx. Again, we'll make use of our integration by substitution method. Quickly, we let u be equated to be the inner function, which in this case is 2x squared plus 1. Our du, therefore, that is the derivative of our function u, would be 4x. That is 2 times 2. Of course, 2 minus 1 here gives us 1. So we have 4x. Du dx is 4x. To get our du, if we did a cross multiply, we would have 4x dx. And again, if we take a look at our original equation, we'll find that we already have 4x dx. Hence, all we need to do is a simple substitution of our du as we go about simplifying our given question here to be in the format f of u du. Let's go ahead to simplify this. We therefore say that our question becomes the integral of u raised to the power minus half. Of course, our roots here, by the laws of indices, can be expressed as a power of half. And since it is a denominator, we simply raise it up to a negative power. Hence, we have all of this, which is equated as our u, as u raised to the power minus half. So u raised to the power minus half, du. Our du here represents 4x dx. So here's our simple equation. If we go ahead to work on this, we would have u raised to the power minus half plus 1 all over minus half plus 1. All of that plus c. And this would give us 2u raised to the power half plus c. And finally, we'll simply impute our original value of u, which is 2x squared plus 1, back into our answer here to get our final answer. To do that, we would have 2 times 2x squared plus 1, all raised to the power half, plus c. We can also bring back our root sign to have 2 root 2x squared plus 1, plus c. And this is our final answer. Now, another very also important method used in integration is what we call the integration by parts. The integration by parts is a technique that relates the integral of a product of two functions to the integral of their derivative and antiderivative. So if we have a product of two functions, in order to solve them, we'll simply equate one to be its derivative, while we equate the other to be the antiderivative. And hence, we go ahead to solve this by simply using a formula uv minus the integral of v du. Let's go on to better understand. When we have a function that is the product of two functions, f of x and the derivative of gx, what we do is to convert it first to this format, f of u dv, by substituting u for f of x and also substituting dv for the g prime, that is the derivative of gx dx. We therefore find the du of our u to be the prime, that is the derivative of f of x dx, while we'll find our v from the integral of the derivative of gx dx. We evaluate our new equation as f of u dv to be uv minus the integral of f of v du. And finally, we replace all that we need to replace, u by f of x, v by the integral of the derivative of gx dx, and du finally by the derivative of f of x dx. It may all seem so complex, but as we carry out some examples, we'll understand exactly how the integration by parts works. Let's take a typical example. Now we have two functions here, and we've been asked to integrate x squared multiplied by the exponential raised to the power x dx. These are two functions. and we want to find their integral. To do this, we'll simply let u be x squared, while we let our dv be the exponential of x dx. Remember we said when we have this kind of functions, we quickly equate them. One to be u, as in this instance, while we equate the other one left to be the dv. So we have our u, which we chose as our x squared, and we have our dv, which we chose as the function left over, e raised to power x dx, exponential raised to power x dx. Therefore, the du, that's the derivative of our u, which we chose to be x squared, is 2x. Du dx is 2x, while our du, which we'll seek in the course of our equation. Remember, our equation is uv minus the integral of v du. So we know what u is, but we don't know what v is. Though we know what our dv is from our dv, which is the derivative of v, is what is equated to be our exponential raised to power x. We can therefore integrate our derivative to get the original function v. Remember. So, du therefore, which we will need later on, would become 2x, if we did a cross multiply here, will become 2x dx. And v, which we also need in the course of our formula, will be the integral of this derivative here. That is the integral of exponential raised to power x dx. And of course, the integral of exponential raised to power x dx will always give us the same thing. So we simply have v as e exponential raised to power x. Now we have all that we require to fit into this formula to solve our equation by parts. We have u is x squared. We have our v, which we have found. Our v is e raised to power x, is exponential raised to power x. And we have our du. Our du we found to be 2x dx. Let's impute all our values within the formula. So when we do that, that is our formula is u dv, which is equals to uv minus the integral of v du. This is our integration by parts formula. When we impute our values, we'll have uv. U here is what? X squared. V here, which we found is what? This. Exponential raised to the power x. Minus the integral of v, the integral of this, multiplied by du. Our du is what? 2x dx. So this is what we have to evaluate. Let's keep this equation aside. We need to find the integration now that we have from our equation here. We have another integration. This is another quick example. This is where it may get a bit complex. In the course of using our integration by parts, sometimes we have to do double integration. As you go ahead, you find that sometimes you may need to do your integration either by parts or by substitutions, maybe more than once, 2 or 3 times. So it's a bit long and tedious, but at the end of the day, we finally get our answer. So let's go on. Integrating v du, which is our integral of e raised to the power x times 2x dx. We integrate this by parts again. So again, we go through the same process. Let u be 2x in this case. And let du, our du will be what? 2 dx. That is, du dx is 2. So our du, therefore, if we cross multiply, would give us du is equals to 2 dx. That's how we came across this 2 dx. So du is 2 dx. Our dv, therefore, we have chosen to be what? E raised to power x. exponential raised to the power x dx. To get, therefore, v alone, this is a derivative. To get the original function, we need to integrate dv, which is this. So we integrate this guy here. We integrate our e raised to the power x, and that gives us the same thing, our exponential raised to the power x. So we have v, which we need in our equation. We have du, and we have u. Let's put it back into our equation here. And that would give us 2x times e raised to the power x minus 2, which comes outside, multiplied by e raised to the power x. So we want to integrate again by parts, if we remember, the v du part of our initial equation 1 here. We have all that we require. Remember our formula, uv minus the integral of v du. We have u as 2x. We have our v, which we found to be exponential raised to the power x. We have our du, which we also have as 2 dx. Let's quickly write out our equation. So we have 2x as u, v, our v again, the integral of our v, and our du. We have this other equation. Let's call this equation 2. If we worked this out, we'll have 2x times our exponential raised to the power x, 2x times this, minus 2, which is a constant. We take it out, and we have the integral of our exponential raised to the power x left. This, of course, would work out to also the integral of this dx is same as this. So we have the value for this, which is e raised to the power, exponential raised to the power x. So all of this becomes 2x times e raised to the power x here minus 2 e raised to the power x plus c. This is the solution of our equation 2. So we have the v du of our original equation 1. Now we can fit in this value into our v du, which is the second part of our equation 1 here. Let's quickly do that. So all of this equation 1 becomes x squared multiplied by e raised to the power x minus our v du we've been found to be all in bracket 2x multiplied by e raised to the power x minus 2 multiplied by e raised to the power x plus c. If we simplify this, we'd have x squared multiplied by e raised to the power x minus 2x multiplied by e raised to the power x plus 2 exponential raised to the power x plus c. And this, at the end of the day, is our final answer. We'll take one more example for better understanding. If we were asked to find the integral of x cubed multiplied by the square root of 4 minus x squared dx, the integral of all of that. Quickly, we see that we have two functions. So we said integration by parts. We use it mostly where we have the product of two functions. And to do that, we said we equate one of those functions to be u, while we equate the other function to be the v. That is a derivative. And at the end of the day, we get uv minus the integral of v du. This is the formula for integration by parts. Let's always keep that at the back of our minds for easy solution to our work. Now let's go ahead and tackle this problem that we've been asked to solve. We were asked to find the integral of x cubed multiplied by the square root of 4 minus x squared dx. Now we need to choose our u. Our u here is x cubed. But we need to be smart. Instead of taking all of the x cubed, we could take the x squared and have an x left over. So if we let u be x squared, it means that whatever is left over is supposed to be our dv. We are supposed to equate that to be dv. The dv now would be the square root of 4 minus x squared times the remaining x that was meant to be in the x cubed. So we have the dv as x multiplied by the square root of 4 minus x squared. We do this so that during the course of our calculations, when we have a problem that we can solve by substitution method, our x will stand for the part that is the derivative of our inner function from what we learned in substitution method, if we remember. So that's why we take x squared and we leave x to be part of our dv. As we work this, we'll get to understand why we separated them. But let's quickly go on. If we have u as our x squared, the derivative of u, of course, we know to be 2x. And to get our v, where we already have, this is the dx, where we already have dv as x times the square root of 4 minus x squared dx. To get our v, we simply find the integral of all of these derivatives. And so we have the integral of x times the square root of 4 minus x squared dx. Let's go on to try and find our v. Now to find our v, this of itself, we also need to solve using the substitution method of integration to find v. And to do this, we say let u be the inner function. Again, now we are doing another substitution within a substitution. It can get a bit complex, but if you are patient, you will get your answer. So let u be our inner function here, which is 4 minus x squared. Du dx, that is the derivative of our u, 4 minus x squared, would be what? Minus 2x. This, the derivative of 4 will give us 0, while our power here comes down, and we are left with x raised to the power 1, of course, which remains x, so we have minus 2x. So du dx here is minus 2x. We need to find the du that will equate or stand for our x dx within our question there. If we do a cross multiplication, we would have our dx come up and our minus 2 come down. We have x dx to be minus 1 over 2 du. So we replace our x dx here, which is x dx, with all of this. And that's how we come about this. Remember, we're working with integration by substitution. To get our v, we're still trying to get our v. So we have this as a simpler form of all of this. Let's see if we can solve this. So we have our minus 1 over 2 come out, and we have u raised to the power half du. This would give us minus 1 over 2. This, of course, half plus 1 would give us 3 over 2, all over 3 over 2. And this would be what? Minus 1 over 3. 2 comes up here, and they cancel out. So we have minus 1 over 3, u raised to the power 3 over 2. And this, if we equate what our original u was, 4 minus x squared. If we equate it back, this is what we have. So our v here that we were looking for will found to be minus 1 over 3 multiplied by 4 minus x squared, all raised to the power 3 over 2. So we have a value for our v. Now, let's equate our original equation, our integration by parts. We have everything we require to do this. We have our u, which we said is x squared. We have our v, which we found to be this. We have our du, which we said is 2x. Let's equate all of these values into our original integration by parts equation. To do that, we would have x squared, which is u, minus 1 over 3 bracket 4 minus x squared all over 3 over 2. All of this is v. This is u. This is v. Minus, next we have the integral, which is this, of v. Again, this is v. We put all of this as v. And then we have du. Our du, we said, is 2x. And this is du. Let's call all of this our equation 1. So this is the solution of the question we were asked from the beginning. Let's see if we can solve all of this out. So if we simplified all of this, we'll come down here to also have another occasion to find the integral again. So we find that sometimes in integration by parts, we keep integrating until we have a solution. Let's quickly again see how we go about this. If we look at our integral here, we need to use the integration by substitution method to find this. So we have our v du to be 1 over 3. Minus 1 over 3 is taken out. So we have minus 1 over 3. And we have u. Let u represent our inner function, 4 minus x. All of that is raised to power 3 over 2. Our du represents 2x dx. That is, if we find the derivative of our inner function u here, if this is u, 4 minus x is u, du dx, 4 minus x squared. If u is 4 minus x squared, du dx will be minus 2x. And therefore, du would be minus 2x dx. So we have our minus here, 2x dx here, represented by du. So our 1 over 3 goes out alone. Our minus stays behind. So minus 2x dx. Minus 2x dx. We represent it with du. So we have our du and we have our u. Hence we have u raised to power 3 over 2. All of this is u raised to power 3 over 2 du. And if we work this out, if we put back our original value of u, we would have all of this minus x squared times 4x minus x squared raised to power 3 over 2 all over 3. That is all of this from this minus our integral v du. And it is minus 1 over 3. Where the integral here would give us u raised to power 3 over 2 plus 1, which is 5 over 2. So 5 over 2 power all over 5 over 2. If we impute back the original value u, which is 4 minus x, we would have this. So this is our v du. All of this is our integral of our v du. Now we have a straightforward equation without another integral. We can simply simplify all we have, and if we do that, we'd have minus x squared over 3 bracket 4 minus x squared all raised to power 3 over 2 minus 2 over 15. If we worked this out, 2 comes here, comes up, and we have 3 times 5, which is minus 2 over 15. in bracket 4 minus x squared raised to power 5 over 2 plus c, which is our constant of integration. Very long, but at the end of the day, we come to our final answer. In summary, let's look at what we've learned today. We've learned that calculus is the mathematical study of change. We also said that calculus has two main branches: integral calculus and the differential calculus. In our class today, we focused on integral calculus. We said that the operation of integration, also known as integral calculus, is the reverse operation of differentiation. That is the inverse or the opposite of differentiation. So if you integrate the derivative of an original function, you get back the original function. Hence, the integral calculus sometimes is referred to as anti-differentiation. Next, we learned about a typical outlay of what the integral process looks like. We broke it down to show that f of x there is called the integration variable, while c is called our constant of integration that follows every integral solution. We also said that our integral sign is basically a stylishly elongated x, which stands for sum. And finally, we said the function within our integral, f of x, is called the integrand. We looked at some rules that govern integration, and one of the first rules we looked at is the integral of a constant. We said the integral of a constant, for instance, c, would give us cx, that is c multiplied by the variable x, plus our constant of integration c. Next, we also looked at the integral of the power of x. We said if we have a variable x raised to a power n and we're asked to find the integral of that variable, we would have x with our power added to 1. That is, if the power is n, we have x raised to the power n plus 1, and we divide all of that by the new number, which is our power n plus 1. And finally, we add for all of that our constant of integration c. Next, we looked at the integral of sum and difference rule. We said that when we have the integral of a function added or subtracted from another function, we'll simply find the individual integral of each summand, and we add or subtract them at the end of the day as the case may seem. Finally, we looked at the methods of integration. We focused on two methods. One of those methods was the integration by substitution method. We said when we have the case of a function of a function, that is an inner function with an external function, multiplied by the derivative of our inner function. When we have such a function, we're asked to find the integral of such functions. We first convert it to a form that is the integral of f of u. We equate our u to be the inner function, the integral of f of u du. We evaluate that, and then we replace our u with the original function that we changed. Next, we looked at another method of integration known as the integration by parts. We said we make use of the integration by parts when we have two functions multiplied together. To make use of this method, we said we equate one of those functions to be u, while we equate the other functions to be dv. dv here being the derivative of a function that we hope to get back later on. So, if we equate that, we'd have the integral of f of u dv. And we said that is equal to uv minus the integral of the function v multiplied by the derivative du. We said that when we evaluate all of that, we'll finally equate back whatever our u represented from the beginning back into our equation, and we have our final answer. Now let's take a look at one or two questions to ascertain if we have really learned what we ought to learn today. We're going to look at one simple example. If we're asked to find the integral x all over the square root of x squared minus 4 dx. If we're asked to find this integral, how would we go about this? What formula do you think we would use? So we'll simply use integration by substitution. Let's quickly start. We say let u be equal to x squared minus 4. It means that the derivative of u with respect to x would be what? 2x. It also means that our du would be 2x dx. It means also that x dx, which we seek to replace in this equation, would be du all over 2, which is same as 1 over 2 du. Next, we impute our values in our substitution method. Remember, in the substitution method, we said we make whatever question we're asked simpler by simply finding our f u du. So let's write this our equation in this format. We simply have our u. U in this case we said is x squared minus 4. But since we have a root x squared minus 4 and it is a denominator, it simply means that we can rewrite our u using the laws of indices to be u raised to power minus half. And of course our du. Our du, we said, represents our x dx, and our du here is actually 1 over 2 du. So we have du over 2, or 1 over 2, and all of this. Of course, 1 over 2 is a constant, hence we take it out of our integral, and we have u raised to power minus half du. If we go ahead to solve this, we'd have 1 over 2. The integral of u raised to power minus half would be u. Minus half plus 1 would give us half. And of course, we also divide all of that by half. And of course, we add our plus c. This can be further simplified to give us 2u raised to power half plus c. Of course, our 2 here comes up, and that's why we have that. 2 again cancels out. I would have u raised to power half plus c. Now, let's replace the original value of u that we equated from the beginning. U here we said is x squared minus 4. So we have x squared minus 4 all raised to power half plus c. We can also rewrite this. A power half, of course, means square root. So if we rewrite this, we would have the square root of x squared minus 4 plus c. And this is our final answer. If we look at our options here, we'll find out that C is our final answer. Now let's take a look at another problem. If we're asked to integrate two functions, I did the product of two functions, we have x plus 1 and x plus 2 raised to power 6. Quickly, from what we've learned, such situations we use the integration by parts method to solve them. Let's quickly jump into our solution. To do this, remember, we would equate this to be f of u dv to be uv minus the integral of v du. This is the formula that we need to remember. So we quickly need to find one of these functions and equate them to u, while we equate the remaining function dx to be dv. To do that, let's select u to be x plus 1. It therefore means that the other function left over would be dv. That is our derivative. Of course, that would be x plus 2 raised to power 6 dx. Our du dx here would become 1. The derivative of 1, of course, is 0. The derivative of x will give us 1. So du dx is 1, and hence du is dx. If we did a cross multiply, du is dx. So we can replace our dx with du in the course of our solution. Next, we need to find our v. All we need to do is to find the integral of our derivative, which is dv, to get our v. And that means we'll find the integral of x plus 2 raised to the power 6 dx. So we have another integration problem here to solve. Let's quickly go ahead to solve that. In this case again, we need to apply the integration by parts formula. V here, we can quickly get, using the substitution method, we simply have this to be x plus 2 raised to the power 7 all over 7. That's our v. So we have all that we need to plug into our original equation or our original formula. If we quickly plug that in, we would have u here, which is x plus 1, multiplied by v. We said our v is what? X plus 2 raised to the power 7 all over 7 minus the integral of v. V is what? X plus 2 raised to the power 7 all over 7. And then we have du. We said our du here is dx. So we have dx. So here we notice that we have another integral problem to solve. To quickly do this, we'll have all of this as 1 over 7 x plus 1 bracket x plus 2 raised to the power 7 minus the integral of this would give us 1 over 7 comes out, our 7 here, and then we find the integration of x plus 2 raised to the power 7 dx. If we work this out, we'll still have this as minus 1 over 7 x plus 2 raised to the power 7. The integral of this would give us x plus 2 raised to the power 8, that is 7 plus 1, all over 8 plus c. So we have something that no longer has an integral sign that we can simply simplify. And to further simplify this, we would have 1 over 7 x plus 1 x plus 2 raised to the power 7 minus 7 times 8 is 56, so we have 1 over 56 multiplied by x plus 2, all of this raised to the power 8 plus c. If we brought out like terms, we would have 1 over 56. All of this, we have 8 here. X plus 1 x plus 2 raised to power 7 minus x plus 2 raised to power 8, plus c. And if we worked all of this out, we'll have a final answer, 1 over 56, x plus 2 raised to power 7 multiplied by 7x plus 6 plus c. This is our final answer. If we take a look at our options, only one correct answer can be found. And that correct answer is D. So D has it. Thank you for your time. I'm sure you had a great time. It was a pleasure for me taking you, and I look forward to having you in our next series in our class. It's Desmond Edagese again, and I'll see you later. Bye. 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 Bye.